This is the first pure astrophysics lecture. What is meant by that? We will be using what we learned until now about the world. For example, how to find distances, periods, Kepler's and Newton's laws, the properties of light in finding what stars are made of, and how the universe works. Soon enough, we will even encounter that famous Einstein formula, E equals mc squared. Note that we have skipped chapters 4 through 8. These are about the solar system constituents. That's covered at Baker in a class called the Solar System, PC 141. In that class we learn the first 3 chapters, and then we use the same tools to learn about our solar system only, not the rest of the universe. Okay, so we are now in chapter 9, and we will also cover chapter 10 towards the end of this week. This picture in the first slide is a picture of the sun through an H-alpha filter. What it means is that our Roy G. Biv colors of the sun, the rainbow colors of the sun, are not all included. Only the orange light at 656 nanometers between wave crests is represented. That is light whose wavelength is 656 over 1 billion meters between wave crests. The visible part of the spectrum include that the visible part of the spectrum is between about 380 and 780 nanometers. At this point in a course, it would not be a bad idea to have several of your PowerPoint presentations open at the same time. I will refer to other lectures and assignments like crazy. What we know is in the table on this slide. This is the basic information about our star, the sun. But how do we know that? For example, how do we know the first value, the size of the sun? Well, you guys figured it out in Lab 1 using values that we found out in Lecture 2 and also later on in Lecture 6. Lecture 2, our Starkest values. Lecture 6, the transit of Venus values. The mass? Look at page 39 in your textbook. After reworking Kepler's third law that related the periods of planets around the sun with their distance from the sun, and using Newton's law about gravity, we can use the two of them to find the mass. For example, you take a mass of a rock and take a smaller rock that orbits it, and from them you can find out, using Kepler's law, the relationship. Then that rock may be orbiting the moon may be orbiting the earth may be orbiting the sun, and that's how you can build up from smaller to larger what the mass of the sun is. And that's a huge number. When we're talking about 210 to the 30, that's basically 2 million trillion kilogram, or 2 million billion trillion tons, metric tons. How about density? Density of water, for example, is 1,000 kilograms per meter cubed. So the sun is a tad denser than water. Finding density, that's easy. Take the sun and dunk it in a bathtub. Find out how much water is displaced. And that's the volume. And mass per volume is density. Okay. Tough to dunk the sun into a bathtub, but you can find its volume with some mathematics. Rotation period? Well, the sun has those spots on it. As we look at the sun one day, then the other day, these spots are moving. What about the temperature? We have learned Wien's law, W-I-E-N. Wien's law basically relates the temperature to the peak of the spectrum. How about the power, the luminosity? There's that Stefan law, and that can help us out find the power by knowing the area of the sun and the temperature. Here is another way by which we can find the power from the sun. Basically, you can place a tub of water on Earth and see by how much the temperature rises in every minute. You just put it in the sun. You then figure out, hey, this tub intersects part of the sunlight, and you can just say, hey, around that sun we have a surface. The area of the surface using mathematics is some sort of a formula called 4 pi r square. No, you don't have to remember that. You take basically the power that entered that specific position and multiply by the whole area, and you found the power. Of course, we're assuming that the sun output is fairly constant, which we found out that it is. Next, we will discuss the structure of the sun. That's a harder sell to make. How do we actually know that the sun has a core, radiation zone, convection zone, photosphere, chromosphere, and after a little transition zone, a corona? I will show in the next couple of slides that the corona can be used with the services of either artificial or natural eclipses. The chromosphere can be investigated with the help of spectroscopy, that is, using of prism-like devices, and the photosphere, the same thing. You can click back and forth between the two pictures on this slide. In the first picture, it is a visible spectrum. That's why underneath the picture you see that it says a V. You would notice that there is radio, infrared, visible, ultraviolet, X-ray, and gamma rays under each picture, including the picture 2 slides back from this one. And you will notice that in a second picture you see way more details. The first picture is taken during a solar eclipse, that is, the sun is behind the moon. That's why the part of the sun that's usually very faint and cannot be seen at all suddenly shows up. In a second picture, an artificial eclipse is created, and you can see the ultraviolet radiation and a lot of details of what happens in the corona region of the sun. In the first picture, you can see a full spectrum of the sun. In the second picture, this is the same exact thing, only the difference is that you can see the intensity at each and every part of the spectrum. Also, the second picture includes the infrared and a little bit of the ultraviolet, whereas the first doesn't. Notice the numbers. The numbers represent the wavelength, which represents the color, and that's in the unit of nanometers. You can see in the second picture that the peak is at around 500 nanometers. That is how we find out the temperature of the sun. The peak represents the temperature. Actually, even the bytes from that continuous spectrum, which we see in the first picture as lines, even those can tell us a little bit about the temperature. The width is a result to a certain extent of that temperature. Okay, maybe it is fairly straightforward to find out what happens at the surface of the sun. But what about the internal regions? Recently, a neat technique has been developed over the last 30 or 40 years. Basically, what it is looking what happens to the sun as a result of some vibrations on it. Now think about it. If you have a gong and you slam it, or if you have a cup and you cling it with a fork, it would make very different sounds whether or not there was something in it or not, and also whether that something in it was solid or not so solid. And that's exactly the technique that we are using for finding what is inside the sun. Interestingly enough, like the glass, the outside part of the sun, or so-called the convective layer, is fairly opaque and behaves like that glass, whereas the internal parts all the way to the core are fairly transparent and behave like the inside of a glass. That is how we came up with this interesting structure of the sun. Its core, radiation zone, convection zone, photosphere, chromosphere, corona, and outflowing solar wind made of charged particles that actually intercept Earth. More on that in the next lecture.